This is section 4.3, number 15. We're given a second order differential equation with no damping, and we're given a forcing function of cosine 9t over pi. The corresponding homogeneous equation, we can find its eigenvalues of plus or minus 2i, which means that the solution of the homogeneous problem is some constant cosine of 2t plus a constant times sine of 2t, and I hope getting to this point is easy for you now. The particular solution, if we use complexification or just assume that it's of the form a cosine 9t over 4 plus b sine 9t over 4, one way or the other, the general form of what we'll end up with for a particular solution will look like this. I want to remind you that we have a trigonometric identity that lets us combine cosines and sines as long as their arguments are the same. So here's omega t and omega t. I can combine these to look like a cosine function or a sine function with the same term, therefore the same frequency, but with a phase shift and a new amplitude. And the amplitude is given by the square root of the sum of the squares of the two current amplitudes. So a sum of a sine and a cosine can always be written as just a single cosine. This is important because when we write the general solution, here's the solution of the homogeneous part, here's the particular solution. I can combine this as well, supposing the k1 and k2 are neither one or 0. I can combine these two as well into a single cosine of 2t with a phase shift and some amplitude c that would be the sum of the squares, the square root of the sum of the squares of k1 and k2. But I can put the general solution in this form and the particular part of it, as I did before, in this form with a different phase shift. The reason this is significant is that when we're given a problem like this, it's important that you realize that in the end, our solution will look like a sum of two cosine functions, or a difference if this could potentially be a negative term, sum or difference of two cosine functions with different frequencies. Here, the frequency is 2 over 2 pi. Here, the frequency is 9/4 over 2 pi, or 9 over 8 pi. And as I showed in the previous little screencast about how to compute beating frequencies, whenever we're in a situation where we have a sum of two cosine functions or a difference of two cosine functions, there will be beating, and we can compute the beating frequency as the difference of the two frequencies divided by 2. And so here I've done it in this case, and so our beating frequency in this case will be 1 over 16 pi, and our rapid response is just the average of the two frequencies, the sum divided by 2. In this case we get 17 pi over 4. On the next slide I will make a rough sketch of these things. We can't be too precise with this, but our beating frequency, we should be okay. So next slide. So now, putting this together again, here's our general solution written as concisely as possible, combining things. So I'm just looking at a cosine and another cosine that are being either added or possibly subtracted. And we have already computed the beating frequency is 1 over 16 pi, and the rapid response frequency was 17 frequency was 17 over 4 pi, and that implied that its period was 4 4 pi over 17. So I'm not even going to begin to try to, and I wouldn't expect you to either, making a rough sketch of quantifying this term, but the 16 pi is the major structure, and so you'll see that I have drawn a graph, and I've indicated it's sloppy as can be, but here's 16 pi. And so this is 4 pi, 8 pi, 12 pi, 16 pi, and I've done 2 periods of it, all the way up to 32 pi. The first thing I did was I laid in my beading structure. So just make rough sine functions or cosine functions. In fact, you know, it's rare to think that they actually start at 0 unless the initial conditions were y times 0 is 0. But if we started over here and we could draw it shifted, it would be fine. But it's fine to assume that we're at 0 just to make a sketch. So I'm drawing my envelope, my 2 beading functions, a positive 1 and a negative 1. And then I have no idea how accurate this is, but the rapid frequency is rapid. It's significantly faster than the beating frequency, and that's all I need to see. Okay, that's it.